Welcome to our lectures that revolve around the basics of hemodynamics. With our set of lectures that are forthcoming, we'll learn how to identify stroke volumes and cardiac outputs. We'll look how to apply the continuity equation in the clinical environment. We'll use our hemodynamic calculations to work out regurgitant volumes and regurgitant fractions to assess valve lesions. We'll understand and learn how to manipulate the Bernoulli equation and how this actually works with pressure gradients. We'll also apply our knowledge of hemodynamics to work out stenotic valves. Furthermore, we can use our formulas to work out the severity in cardiac shunting. And finally, we can look at the limitations and the assumptions we use when we have our quantitative analysis. In this particular lecture, we'll be looking at the cardiac cycles. Diastole and systole make two of the components in the cardiac cycle, but these can be further broken down into a total of 6 phases. Pressure waveforms derived from catheter work demonstrate changes within the cardiac chambers nicely. We can also see the opening and closing of cardiac valves and the actual phases of the cardiac cycle. With the concepts of flow, we'll learn what cardiac output is, then how we determine flow when it's not continuous or constant. Lastly, we'll step into pressure gradients, the Bernoulli equation, and the relationship between pressure and velocity. We'll explore how we came to find a simple formula that a change in pressure is equal to 4 times the velocity squared. In its simplest terms, hemodynamics is the understanding of blood flow within the heart and the circulatory system. We assess pressure and volumes and the structural findings associated with these. So why is there actually flow? Blood volumes with high pressure will always move to areas of low pressure to establish equilibrium. And this can occur in one of two ways. One, the heart chamber generates pressure that drives blood into a chamber of low pressure. And this is what we actually see in the ventricles in systole. The other is one heart chamber decreases in pressure that passively draws blood from another chamber of high pressure. Here we have an example of systole, such as the left ventricle driving blood into the aorta. We can actually see the ventricular muscle thickening and the driving force that ejects the blood into the aorta and therefore out into the body. Then we can see diastole, where left ventricular pressure drops below to the left atrium and the smaller left atrium allows the volume to fall into the left ventricle. So why and how is this all occurring? In systole, the left ventricular depolarization forces the smooth muscle cells to contract. This initiates the isovolemic contraction phase. The ventricle is starting to generate pressure. However, at this stage, the pressure in the left ventricle is still lower than that in the aorta. The second phase of systole is called the ejection period. Left ventricular pressure has overcome that in the aorta and blood starts flowing out. This continues until depolarization of the ventricular cells is complete and move into a refractory period. At this stage, the aorta will be higher pressure than that of the ventricle, which forces the aortic valve shut. Diastole has a few more phases, but follows the same principle. The left ventricular cells enter a process of repolarization, and a state of isovolemic relaxation begins. Pressure is dropping in the left ventricle, but is still higher than that of the left atrium. Basically, we have a state of no flow. The muscle fibers continue to relax in the ventricle and then stretch. Finally, pressure in the left ventricle drops below to the left atrium. This initiates early diastolic or passive filling, and flow occurs until the fibers can stretch no further and pressure increases in the left ventricle. A period of diastasis is then observed, where there is no flow between the chambers, as pressures equalize. Atrial contraction, which corresponds with the P wave on an ECG, pushes a little bit more blood into the ventricle. Consider blowing up a balloon until it's full and the surface is taut. The atrial contraction is like giving just a final little breath. Notice in our diagram how the mitral valve has a double motion to correspond with these phases. and that the atrial contracts late in diastole. And we can see that here clearly. Look for the double motion that we actually see in the mitral valve. And then this very late atrial contraction. Here we have some pressure waveforms superimposed of the left ventricle, left atrium, and the aorta. Note that the IVCT occurs between mitral valve closure and aortic valve opening, this duration here. The ejection period is between the aortic valve opening and aortic valve closure. And then the next phase we move into is diastole. This is between aortic valve closure and mitral valve opening. We have the isovolemic relaxation time. This is then closely followed by early diastolic filling, and we can see that where the left atrial pressure comes above that of the left ventricle, and we get the early diastolic filling. Then this is very much closely followed by a period of the diastasis, where the two lines are superimposed. Finally, we have our A wave here for atrial contraction, where the pressure in the left atrium again rises that above of the left ventricle very briefly. Also note the aortic pressure waveform. When the line is above that of the left ventricle, the aortic valve is shut. The aortic pressure follows that of the left ventricle during the ejection period. Thus, LV systolic pressure is equal to the arterial systolic pressure that is measured with a sphygmo. The dip at AC is the dicrotic notch. In diastole, blood rushes back down towards the aorta, which closes the aortic valve and then also fills the coronary arteries with blood. So, an important thing to note is there's forward blood flow in the coronary arteries in diastole. So, what occurs in the vessel? And what would happen if the vessel was stenotic? Well, we can assess flow through the vessel as depicted here. Flow is equal to the velocity multiplied by the cross-sectional area. So we term flow to be Q, velocity here, and cross-sectional area. So cross-sectional area, what we can measure is that there. So cross-sectional area is equal to pi times the radius squared. We know pi is equal to 3.14. And then what we can do is rearrange our calculation to make it a little bit simpler. So 3.14 divided by 4 times the diameter squared. So we're dividing by 4 because we're moving from a radius squared to diameter squared. This now gives us our nice little formula of cross-sectional area is equal to 0.785 times the diameter squared. So in echo, it's much easier to measure a diameter than try and work out what a radius may be, such as of the LVOT or the RVOT. So consider our tube. If flow Q stays the same and velocity increases, then the cross-sectional area has to decrease proportionally. They're locked in this formula. If the cross-sectional area and V stays the same, then Q must decrease accordingly. This all revolves around algebra and understanding that when the variable moves through the equal side to be on the other side, a multiplication becomes a division and an addition becomes a subtraction. And we can see that with our equation here. So flow is equal to velocity times cross-sectional area. If we want to work out the cross-sectional area, it's Q divided by velocity. Velocity has moved on to the other side of the equation. And conversely, if we wanted to work out velocity, velocity is equal to Q divided by cross-sectional area. Cross-sectional area has moved on to the other side of the equation. But considering in cardiac flows that motion isn't always constant. To account for this, we measure the velocity time integral, or VTI. A flow is obtained in a Doppler spectral trace, and the user will trace an outline around the flow to measure the area between the tracing and the baseline. So as we could imagine here, we would trace the outer brighter edge capturing all the velocities within the curve there for the period of time. So what we're doing here is we're measuring velocities expressed as centimeters per second and measuring over time in seconds. So what we would have is centimeters per second divided by seconds. So basically the seconds cancel out, and our unit of measure for velocity time integral is centimeters. Our original calculation can then be modified. So a very simplified approach that flow is equal to velocity times the cross-section area then moves to a more valuable calculation that we can actually use in a clinical environment, where we talk about stroke volumes. So stroke volume is equal to the velocity time integral times the cross-sectional area. So stroke volume then is essentially the amount of blood that's actually moving through a cardiac cycle, each an individual heartbeat. Cardiac output is a common and important factor in determining heart function. It is the composite of heart rate and stroke volume. So we can see here, cardiac output is equal to heart rate times stroke volume. And we know already that stroke volume is equal to velocity time integral and the cross-sectional area. So expanding our formulas, we get cross-sectional area is equal to the heart rate times velocity time integral times cross-sectional area. We must be aware, though, that the above calculation is represented in milliliters, mils. We like to present outputs in liters. Thus, we must divide our result by 1,000 to correct the units for the measure. Volumetric calculations play an important part in hemodynamics, and we'll discuss this further in our later lectures. The determination of pressure gradients plays an integral part of an echo exam. The Bernoulli equation is applied to demonstrate these changes in pressures. Consider our tube from before, but now there is a kink in the middle. The Bernoulli equation applies the conservation of energy principle. The amount of energy or blood flow has to be uniform through the wide and narrow sections of the tube. Blood in the wide section is moving with relatively low velocity and high pressure. As blood moves to the narrowing, it speeds up. So to maintain its uniform energy, the pressure must therefore decrease. Important thing to note here is pressure and velocity are inversely related. So high pressure is low velocity. High velocity means low pressure. Since the pressure has dropped at the narrowing, we're now able to derive a pressure gradient. A change in pressure has occurred. The simplified Bernoulli equation presents as a change in pressure is equal to 4 times the velocity squared. But where did this actually come from? The Bernoulli equation in its full form shows that a pressure difference is equal to convective acceleration plus flow acceleration plus viscous friction. To expand this mathematically is a bit of an eyesore, which we won't delve into. However, we can see much more than 4v squared is at play here. So how does this actually all simplify? Well, flow acceleration is zero at peak velocity. It's at the highest point, so it's not accelerating anymore. Thus, this component can be ignored from our cardiac calculation. Viscous friction is effectively negligible, and flow profiles in a center of the vessel are flat. This then leaves convective acceleration, which is half the density of blood, which is the little p symbol there, times the velocity at the narrowing point squared minus the velocity in the wide area squared. Half the density of blood closely approximates 4, and in most instances, the first velocity in the wider area, or the proximal velocity, is small and calculates to an insignificantly small value. Thus, we end up with our change in pressure is equal to 4v squared. The important thing to note here is we're determining pressure gradients, the change in pressure at a narrowing in a vessel or between two cardiac chambers, not the pressure within the chamber itself. I've mentioned that proximal velocities are usually ignored. However, when flow rates higher than 1.2 meters per second are in play, they are considered significant and can't be ignored as they influence the equation, leading to an overestimation of the true pressure gradient. So to account for that, we include it in the calculation. So a change in pressure is equal to 4 times the velocity at the narrowing squared minus the proximal velocity squared. So with this, we've touched on the basics of hemodynamics, the cardiac cycles and the flow occurring, and how the blood tries to establish equilibrium by moving from high pressure environments to low areas. And we can see that many of the principles behind what we're actually going to learn are strongly tied up in mathematics. I'll try and move slowly through the complex stuff and expand upon all the workings to simplify the process. Getting lost in a field of numbers and variables is easily done, and many of the principles ahead are actually very closely related. You may want to flag certain points within a lecture or come back and replay previous lecture to help bring concepts together.